First of all, introducing displacement time graphs, and really these are best to be done just by considering some examples. So displacement time, a graph of S versus T, S in meters, T in seconds. Remember, even if you're doing sketch graphs, these labels are important. And I'll just make up some examples. So if we look at some simple examples to start with, if we had a displacement time graph which looked like that, then you've got to just assume that's a straight line. It's hard to draw with a rule on my iPad. What does that show? Well, if we look at that, at 1 second, the displacement of this object is 2 meters. At 2 seconds, the displacement is 2 meters. At 3 seconds, the displacement is 2 meters. So this is an example of an object which is not changing its displacement, i.e. it's stationary. And it doesn't actually matter whether that was 1 meter, 2 meters, 3 meters, whatever. If you have a flat line in a displacement time graph, then the displacement isn't changing, the object is stationary. Next example, and I'll just draw this quickly to save a bit of time. Okay, so the next one, try and draw it like that. And the idea is to look at the displacement here after 1 second is 0.5 meters, after 2 seconds 1 meter, after 3 seconds it's 1.5 meters. So this object is moving by 0.5 meters every second, i.e. it has a constant velocity. The displacement is increasing by a fixed amount every second. If we looked at it for a different constant velocity, we'll contrast that a wee bit. If, for instance, it covered 1 meter in the first second, 1 meter in the second, and 1 meter in the third, and that would look like that. I've drawn it well. 1 meter in the first second, another meter in the second, another meter in the third. Then that's also a constant velocity, but it's a larger velocity compared to the red one. So the red one, remember, was going 0.5 meters every second. The green one's going 1 meter every second. So it shows a larger velocity. And what we see is that the line there is steeper. Okay, so a steeper gradient, right, a steeper line. A steeper line, or a larger gradient, shows a larger velocity. We'll come back to that concept when we think about the links between the different graphs. And then the last one I'm going to try and draw is if this was a curve, if the displacement was a curve. I'm going to put in a couple of guide dots just to try and help me a wee bit here. And what I'm trying to get, I don't think my scale's particularly regular to start with, is it? Is a curve. Yeah, I've not drawn it particularly great. But basically what this curve shows, if you look at the first second, it travelled 0.5 metres. But in the next second it went from 0.5 up to 1.5, so it travelled 1 metre. And in the next second it went from 1.5 up to 3, so it travelled 1.5 metres. And so what's happening there is the displacement's getting bigger every second. 0.5, 1, 1.5. So what we have there is an acceleration. Now we can't really tell initially if that's a constant acceleration or not, but given that that's what we deal with at higher, we only really look at constant accelerations. I've set this one up so that it is. And these graphs incidentally do also tie in with the equations of motion that we've done. And what you're seeing here is an example of an s equals ut plus a half at squared curve. Right, so that shows that when objects accelerating, it started at 0 velocity in this example, but you're getting the half at squared curve. The velocity graph, the previous one, sorry, showing a constant velocity, is an example of s equals vt, the constant velocity equation. Right. So, another way of looking at this, it ties in with the previous graph that we'll look at, is if you look at the steepness of the line at each point, and then if I kind of try and sketch a tangent there at that point, can you see that the line is getting steeper at each of these points where I draw a tangent? And that steeper line once again shows a larger velocity, it shows you the velocity getting larger. And remember, velocity is to displacement what speed is to distance. So if you were given distance time graphs, then you could apply the same sort of logic as we did here, and you would be talking about constant speeds and larger speeds in the middle one. So I've pre-drawn some of these axes to save a bit of time. And the first one here I've drawn the graph in, and what we've got is a flat line on a velocity time graph. And what we see then is at the first second the velocity is 1, second it's 1, third second it's 1. So on a velocity time graph, this is the shape that we get for constant velocity. If we looked at a different graph, then we might get something like this. And what we're after here is the idea that at the first second, the velocity is 0.5. For the next second, it's 1. For the next second, it's 1.5. So the velocity is increasing by 0.5 every second. So that shows a constant acceleration. And if we looked at a different shape for that, our final one, sorry, same shape, but different steepness. So if we looked at a steeper line, then that is also a constant acceleration. But this time, the velocity is going up by 1 each second. So roughly 1 after 1 second, 2 after 2, 3 after 3. So constant acceleration again, but it's a larger acceleration. Remember, don't use terms like faster acceleration. Okay, faster can be used to describe velocities, but not times or accelerations in kind of formal exam situations. And the only other thing maybe worth pointing out was these two second graphs have both started from 0. If we looked at, get back to the second graph and looked at one like that, maybe I can draw it well. It starts from 1 and then goes up to 1.5 and then up to 2 and then up to 2.5 roughly. Then what we've got is the same constant acceleration. So same acceleration, but just a different starting velocity. So if the lines are parallel, that shows the same acceleration. Steeper lines are larger accelerations. So both of these graphs have the same acceleration. So looking at acceleration time graphs, and generally these are actually quite simple. We've looked at constant velocity, for instance, coming up a couple of times, and the graph, the acceleration time graph for constant velocity, well, if the velocity is constant, there is no acceleration, so the acceleration time graph is simply a flat line along 0. I've just realised the SQA went like that, I've missed out 0 from my axis. If we were to look at another constant acceleration, so a positive value, but staying constant throughout. So these are constant acceleration. And the first one is also constant, but it's this kind of special case of zero acceleration. So let's say these are generally straightforward. I mean, you could in theory get diagonal lines, you could get curves, but they're not part of the higher course, so you shouldn't see them. And the only other idea I thought worth pointing out was that sometimes you'll get kind of a change in the acceleration at some point, but we'll kind of idealise it as kind of an instantaneous change in each section to this motion. Right, so the first 2 seconds, right, are a constant acceleration of 2 meters per second squared. And then we kind of get an instantaneous jump to 3 meters per second squared for the next second, so between 2 and 3 seconds. And in terms of analysing graphs like that, you need to split it up into sections, so you don't have a way of doing that, all of that journey together. We'd have to look at the first 2 seconds on its own, and then look at the next second on its own. So for example, if I wanted to know the velocity after 3 seconds, example, assuming it started from rest. So I would have to look at 1 to 2 seconds first of all, and then I get u equals 0. V is what I'm trying to work out. The acceleration for that first 2 seconds is 2, and the time is also 2. So I can then do my V equals u plus AT equals 0 plus 2 times 2, 4 meters per second. And now I can analyse what goes on in the 2 to 3 seconds. And the u for the 2 to 3 seconds, well, it follows on from what happened in the first 2 seconds, so the u is 4. Right, the velocity at the end of the first section. The v is once again what I'm trying to work out. The acceleration for this section of the motion is 3, and it occurs for a time of 1 second between 2 and 3. So once again I can do v equals u plus AT equals 4 plus 3 times 1, 7 meters per second, and that would be my final answer for the velocity after 3 seconds. So in this one we're going to look at the links between the graphs. So if I'm given an acceleration time graph, can I work out what's going on in the velocity time graph? And then in the displacement time graph, or vice versa, could I work between the different graphs? So an acceleration time graph, which is flat like this, is a constant acceleration, which means the velocity is increasing by 1 every second. If you assume it started from rest here, it could start from a different velocity, but it's a bit easier if I do it starting from rest. Then after 1 second, it will increase to 1 meter per second. And then in the next second, it will increase by another meter per second. And in the next second by another meter per second. So the constant acceleration, remember in the velocity time graph, is that diagonal line. And that's how they're linked together. And basically what we're seeing here, right, is that the gradient of this line, the velocity time graph, is the value of the acceleration. So if I looked at the gradient at that point at 1 second, then I can see that the gradient, right, if I could draw in a wee tangent, I'll do it in a different colour. If I drew in a wee tangent, it has a gradient of 1. If I look at the next second, it has a gradient of 1 still. If I looked at the next second, it has a gradient of 1. Okay, if I could draw these a bit more neatly. So the gradient of this velocity time graph gives you the acceleration. That's the link between the two graphs. I'll get rid of those green lines now that I was just using to talk about. And then we'll write that idea, right, that the gradient of the velocity time graph is the acceleration. And this diagonal line has a constant gradient, the acceleration is constant. If we wanted to go from this velocity to work out what's happening to the displacement, well, remember the displacement is the area under a graph. So the velocity time graph kind of sits in the middle and you can go either way. The area under the velocity time graph is the displacement. So if I look at the area in the first second, it would be a wee triangle like that. And it would be half 1 times 1. So the gradient, I'm going to switch to red. A half 1 times 1 is 0.5. So after 1 second I know the displacement is 0.5. If I were to do the gradient after, sorry I keep saying gradient, that's wrong. If I were to do the displacement after 2 seconds, then that would be that triangle there, that would be my area under graph for the first 2 seconds, would be a triangle, which would be a half times 2 times 2. So that is 2 meters. And if I were to do the same idea for 3 seconds, then my triangle gets expanded again for the first 3 seconds. Big triangle now. And it's a half times 3 times 3. So it would be 4.5, so it's actually off my scale. Maybe somewhere way up there. And so what we get there is the curved lines that we've seen. Not terribly well drawn, but okay, so that's a curve for an object with a constant acceleration, and that ties in with our equation. Once again, s equals ut plus a half at squared. This graph, remember, ties in with v equals u plus at. So they're linked together, and these two bits in green here are how all these graphs are linked together. And with the displacement time graph, I can also use the idea, so I've kind of gone from velocity to displacement. I could go the other way as well. And remember that is, we looked at this earlier, but the gradient of the displacement time graph is the velocity. So once again, if I looked at how steep that line is at that point, and then at that point, and then getting even steeper, then that ties in with the idea that the velocity is increasing. So that would be a gradient of 0.5, of 1. That would be a gradient of 2. That would be a gradient of 3, because the velocity is going from 1 to 2 to 3 in those first 3 seconds. So what we've been dealing with up to now has been fairly abstract, just trying to introduce the basic ideas of how these graphs are linked together. We're going to go on to look at more real-world examples, so practical examples. But also we've got to introduce one other idea, and that is a change in direction. Everything that we've looked at up to now has just been considering an object going in one direction. And remember, we show changes in direction in physics as velocity is going from positive to negative. The negative simply indicates in the opposite direction, so usually, for instance, up is positive, down is negative. So these graphs that we're going to look at have to have bits below the origin as well. Oops, that's not my origin. So you've got to have negative parts to your y-axis as well to show that. time will always be positive. It's a scalar quantity. So this example is what would happen if you threw an object straight up the way. So in this example, it's thrown up at just below 20 meters per second. And what would happen, you know, if you threw an object up the way, then it's got positive velocity, but the acceleration is pulling it down because of gravity. So it's going to decelerate. So during this first section of the motion, we have a positive velocity, i.e. upwards, but we've got a negative gradient or a negative acceleration. So because the velocity is positive and the acceleration is negative, they've got the opposite signs, so the object is going to slow down. So that's on the way up. Right, because of positive velocity, but slowing down because the negative acceleration is acting against that positive velocity. So this here, where it goes, is zero velocity, where it goes from positive velocities to negative. Remember, positive velocities are upwards, negative velocities are downwards. So that is a change in direction, which means it's stopped going up and started to come back down, i.e. that is the highest point. Then on the way down, we've now got negative values of velocity. We've got negative velocities, but we've also got negative acceleration because this line is still sloping down the way. So negative velocities tell us it's on the way down, but because the negative acceleration and the negative velocity are in the same direction, it's speeding up. So remember, at higher, we move away from the idea that negative accelerations always mean slowing down. You've got to be able to deal with the idea that you look at the velocity and acceleration. If they've got the same sign, then the object will be speeding up. Opposite signs, it will be slowing down. And in this case, it's speeding up in a negative direction, i.e. it's speeding up down the way. So it's on the way down and speeding up. And what we see is the corresponding acceleration time graph is always negative, because the gradient of the line above the velocity time graph is always negative as well. So when an object changes from going up to going down, the acceleration doesn't change. And if this was an object in free fall, then that would be minus 9.8. It would always be a negative acceleration. And the other thing that we could consider is displacement. If you considered it on the way up, then the area under graph would be that area there. Sorry, that's the wrong pen tool. So it would be that area there. So roughly here, I'm rounding off the values, but roughly a half times 2 times 20. So that's roughly 10 meters up. But then the area under the graph, the area on the way down is defined as the area between the line and the axis. So it would be that area there. And because that is below the axis, that would be considered a negative area. So the displacement on the way back down would be minus 10 roughly as well. And therefore the total displacement once it's going up and down would be the plus 10 from the first section and the minus 10 from the second section. Now the total displacement would be 0 because the object's gone up and then come back to the same point. So that's how we could consider displacement time in this, but you wouldn't be asked about a displacement time graph. And this last example we'll look at is a bouncing ball. So a ball that's dropped from a height, hits the ground, bounces back up. So here's our starting point here, and if we look at this first section here, can you see we've got negative velocities? I'm just going to use V for velocity. And the line is sloping down, so we have negative acceleration, so negative A. So what you've got there is both of them are negative, so it's speeding up on the way down. So this is where it was dropped at 0 and then it's speeding up. What would cause it to stop speeding up? Well, that's obviously when it hits the ground. So this is the point where it first encounters the ground. But bounces aren't instantaneous. So when a ball starts to hit the ground, then it will start to slow down as the ball kind of crushes, if you've seen high-speed video footage. So here we still have negative velocities. The ball in the hole is still moving down the way, but we've got positive accelerations because it's from the ground. So where we had the falling, it was a minus 9.8, but we don't know what value this acceleration is yet. We could calculate it, but we'll look at a graph of that later. But we've got positive accelerations, so the object is now slowing down, and that's it squashing down. And then we go through 0, and that's when it's reached its lowest point here rather than its highest point. So it's a ball squashed down to a maximum. But then because of its elastic nature, it will start to expand back out again. So now we can see the velocities have changed to be positive v, and the line is sloping up. So this is accelerating back up as the ball re-expands. Once it expands enough, it will leave the ground. Right, that basically energy that was stored as it contracted in its elastic nature is converted back into kinetic energy in the opposite direction, so it leaves the ground. Now in this example, it's a perfect collision. It hit the ground at -9, it leaves the ground at +9. In reality, that wouldn't happen, and you'll see these graphs as well. We're kind of slowly, with these values decreasing at every bounce. So we've now managed to get at that positive +9 velocity. So we've still got a positive velocity at this point, but the gradient is sloping down, so we've got a negative acceleration. So this is it now slowing down on the way up. So the bounce has given it an upward velocity, but because gravity acts down the way, the acceleration due to gravity acts down the way, then it will start slowing down until once again it goes through 0, which is a change in direction because it's reached its highest point. And then the whole cycle starts again. And in this case it would keep going forever because there's no energy lost in the bounce. There's no energy lost due to friction in this particular graph, so it's an idealised graph. But that sort of idea of analysing what's going on in each section is important. It's about looking, are the values of the velocity positive or negative? And is the slope of the line positive or negative? Because that tells you about the acceleration. The corresponding acceleration time graph, if I tried to sketch that without any values, although I could actually put in the -9.8 for when it's accelerating due to gravity. So I would know during that first section it's going to be -9.8. So I'll put a line at -10. So the acceleration would be constant. Getting this idealised graph is it all of a sudden switches to being positive. So at this point the acceleration goes positive, and can you see that this line here is steeper than that line there? So even without knowing that value, I can tell it's got a larger positive. So if that was -10, it's going to be somewhere up above +10. So I don't know its exact value, but I do know that it's a larger value. So if I'm doing a sketch graph, I can show the acceleration at some positive value as long as it's greater. And then once again we get this kind of instantaneous change as the ball leaves the ground and it goes back to our -9.8. And remember, on the way up it's -9.8, on the way down it's -9.8, all the way along to once again when it hits the ground again it bounce. And then we get jump to some large positive value, back to -9.8. So this would be the corresponding acceleration time graph. For that bouncing ball that you're asked to sketch.